The natural question when people hear breakthrough with the inertial confinement, with the magnetic confinement is, so when will we have commercial
Yeah.
um, reactors, power plants that are actually producing electricity? What's your sense, looking out into the future? When do you think you can envision a future where we have actual electricity coming from nuclear fusion?
Partly driven by us, but in other places as well too. So there's the advent. What's so different now than 3 or 4 years ago? Like we launched around 4 years ago. What's so different now is the advent of a very nascent but seemingly robust like commercial fusion, endeavor. So it's not just Commonwealth Fusion Systems. There's something like 20 plus companies.
So there's a sector now.
There's a sector. They actually have something called the Fusion Industry Association, which
Nice.
if your viewers want to go see this describes the different, and they've got this plethora of approaches. Like I haven't even described all the approaches. I've basically described the mainline approaches. And they're all at varying degrees of technical and scientific maturity with very huge different, balances between them. But what they share is that because they're going out and getting funding from the private sector, is that their stated goals are about getting fusion into place so that both it meets the investors' demands, which are interesting, right, and the timescales of that, but also it's like, well, there's going to, and why? It's because it's easy. There's this enormous driver about getting carbon-free energy sources out into the market, and whoever figures those out is going to be it's going to be very important geopolitically, but also economically as well too. So it's a different kind of bet, I guess, or a different kind of gamble that you're taking with fusion, but it's so disruptive that it's like there's essentially a class of investors and teams that are ready to go after it as well too. So what do they share in this? They typically share getting after fusion on a time scale so that could it have any relevance towards climate change, battling climate change? And I would say this is difficult, but it's fairly easy because it's math. So what you do is you actually go to some target like 2050 or 2060, something like this, and say, I want to be blank percent of the world's market of electricity or something like that. And we know historically what it takes to evolve and distribute these kinds of technologies, because every technology takes some period of time. It's a so-called S curve. It's basically everything follows a logarithmic curve, like exponential type curve. It's a straight line, a log plot. And like you look at wind, solar, fission, they all follow the same thing. So it's easy. You take that curve and you go, that slope, and you work backwards. And you go, if you don't start in the early 2030s, like it's not going to have a significant impact by that time. So all of them share this idea. And in fact, it's not just the companies now. The US federal government has a program that was started last year that said we should be looking to try to get like the first, and what do I mean by like, what does it mean to start? That you've got something that's putting electricity on the grid, a pilot, what we call it. And if that can get started like in the early 2030s, the idea of ramping it up, makes sense. And it's math, right?
Yeah.
So that's the ambition. Then the question is, and actually this is different because the government program, and they vary around in this. So for example, the United Kingdom's government idea was to get the first one on by 2040. And China has ambitions probably in middle 2030s, or maybe a little bit later. And Europe, continental Europe, it's a little bit, I'm not exactly sure where it is, but it's like later. It's like 2050 or 2060 because it's mostly linked to the ITER timeline as well too. The fusion companies, which makes sense, it's like, of course they've got the most aggressive timelines. It's like, we're going to map the human genome faster as well too, right? So it's interesting about where we are. And I think, we're not all the way there, but my intuition tells me we're probably going to have a couple of cracks at it actually on that timeline. So this is where we have to be careful, though. You say commercial fusion. What does that mean? Commercial fusion to me means that you actually have a known quantity about what it costs to build, and what it costs to operate, and the reliability of putting energy on the grid. That's commercial fusion. It's like, so it turns out that that's not necessarily exactly the first fusion devices that put electricity on the grid, because there's a learning curve to get like better and better at it. But that's probably, I would suspect, the biggest hurdle is to get to the first one.
The work I've done the work I continue to do with autonomous vehicles and semi-autonomous vehicles. There's an interesting parallel there where a bunch of companies announced a deadline for themselves in 2020, 21, 22, and only a small subset of those companies have actually really pushed that forward. There's Google with Waymo, or Alphabet rather, and then there's Tesla with semi-autonomous driving in their autopilot full self-driving mode. And those are different approaches. So Tesla is achieving much, much higher scale, but the sort of the quality of the drive is semi-autonomous, right? I don't know if there's a metaphor, an analogy here.
Yeah.
And then there's Waymo that's focusing on very specific cities, but achieving real full autonomy with actual passengers, but the scale is much smaller. So I wonder, just like you said, there'll be these kinds of similar kind of really hard pushes.
Absolutely. So actually, this is it's why I'm encouraged about fusion. So fusion's still hard. Let's let everyone be clear, because of the science underneath it of achieving the right conditions for the plasma, basically is a yardstick that you have to put up against all of them. What's encouraging that I see in this, and it's actually what happens when you sort of let loose the creativity of this, is maybe I'll go back to first principles. So fusion is also a fairly strange. So if you think about building a coal plant, like burning wood and coal and gas is actually not that much different from each other, because they're kind of about the same physical conditions, and you get the fuel and you light it. Fusion is very. Remember, I told you that there's this condition of the temperature, which is kind of universal. But if you take the density of the fuel between magnetic fusion and inertial fusion, they're different by about a factor of 10 billion.
Mm-hmm.
So the density of the fuel really matters. And actually, so does this means the energy confinement time is also different by a factor of 10 billion as well, too, because it's the product of those two. So one's really dense and short-lived, and the other one's really long-lived and actually under-dense as well, too. So what that means is that the way to get the underlying physical state is so different among these different approaches. What it lends itself to is, does this mean that eventual commercial products will actually fill different needs in the energy system? So it sort of goes to your comment about, I have to suspect this. It's like, because anything that is high tech and is like a really important thing in our economy tends to never find its way as only one manifestation. Like, look at transportation as well too. We have scooters, Vespas, overland trucks, cars, electric cars. Of course we have these because they meet different demands in it. So what's interesting, that I find fascinating now is that we have in fusion, it's going to look like that probably there's while the near term focuses on electricity production, there might even be different kinds of markets that actually make sense in some places, less in others. It comes to trade-offs, because we haven't really talked about the engineering yet, but the engineering really matters, like to the operation of the device. And so it could be that I suspect what we'll end up with is several different configurations which have different features, which are trade-offs basically in the energy market.
What do you see as the major engineering or general hurdles that are in the way?
Yeah. So the first one is just the cost of building a single unit. So fusion has, and it's actually interesting you talked about the different models that you have. So fusion has one of its interesting limitations is that it's very hard. It almost at some point becomes physically impossible to actually make small power units. Like a kilowatt, 1,000 watts, which is like a personal home, like, is about 1,000 watts, or your personal use of energy of electricity is about like 1,000 watts. This is basically impossible for a single, unit to do this. So like you're not going to have a fusion like power plant like as your furnace or your electric heater in your home. And the reason for this comes from the fact that fusion relies on it being, it's not just that it's very hot, it's that the fusion power is the heating source to keep it hot. So if you go too small, it basically just cannot keep it hot. That's so it's interesting is that this is one of the hard parts. So this means that the individual units, and it varies from concept to concept, but the National Academy's report that came out last year sort of put the benchmark as being like probably the minimum size looks like around 50 million watts of electricity, which is like enough for like a small to, mid-sized city actually.
Mhm.
So that is so that's sort of like a scale challenge, and in fact, it's one of the reasons why in Commonwealth and in other private sector ones, like they try to push this down actually of trying to get to these smaller units, just because it reduces the cost of it. Then probably, obviously, I would say it's an obvious one, like achieving the fusion state itself and high gain is a hard one, but we already talked about.
What kind of hurdle, what kind of challenge
Well,
is that?
that's achieving the right temperature, density, and energy confinement time in the fuel itself, in the plasma itself. And so some of the configurations which are being chosen have quite a ways to go. In fact, I've seen those, but what their consideration is, oh yes, but by our particular configuration, the engineering simplicity confers like an economic advantage, even if we're behind in sort of in a science sense. Okay, which is fine. This is also what you get when you get an explosion in the private sector. You basically are distributing risks in different ways, right? Which makes sense. All of that good. But so what I would say is that the next hurdle to really overcome is about making net electricity. So like we need to see a unit or several units like using fusion in some way to put a meaningful amount of energy on the grid, because this starts giving us real answers as to like what this is going to look like.
The full end-to-end process.
The full end-to-end thing. So Commonwealth's goal is that I'll just comment to Commonwealth because I'll take some credit for this, is that the origins of Commonwealth were in fact in examining that. Like we could see this new technology coming forward, this new superconducting material, and the origins of our thought process were really around designing effectively the pilot plant or the commercial unit. It's called ARC, which is actually the step forward after Spark, and that was the origins of it. So all the things that were other parts of the plant, like Spark and the magnet, were actually all informed totally by building something that's going to put net electricity on the grid. And the timing of that, we still hope, is actually the early 2030s.
So Spark is the design of the tokamak, and ARC is the actual full end-to-end thing.
It is like a thing that actually puts that energy on the grid. So Spark is named, intentionally, that it's like it's on for a short period of time, and it doesn't have it has, it's the spark of the fusion, revolution or something like that, I guess we could call it. So those are sort of the programmatic challenges of doing that. And it's you talked about SpaceX. So what has evolved even in the last year or so was, in fact, in March of 2022, the White House announced that it was going to start a program that kind of looks like a SpaceX analogy, that namely, wow, we've got these things in the private sector. We should leverage the private sector and the advantages of what they obtain, but also with the things like this is going to be hard and it's going to take quite a bit of financing. So why don't we set up a program where we don't really get in the way of the private sector fusion companies, but we help them finance these difficult things, which is how SpaceX basically became successful through the COTS program. Fantastic, right? And that's evolving as well too. So like the fusion ecosystem is almost unrecognizable from where it was like 5 years ago around those things.
How important is it for the heads of the companies that are working on nuclear fusion to have a Twitter account and to be quite? You said you don't use Twitter.
I don't use Twitter
very much. I mean, there is some element to, and I don't think this should be discounted. Whatever you think about figures like Jeff Bezos with Blue Origin or Elon Musk with SpaceX, there is a science communication, to put it in nice terms, that's kind of required to really educate the public and get everybody excited and sell the sexiness of it. I mean, just even the videos of SpaceX, just being able to kind of get everybody excited about going out to space once again. I mean, there's all kinds of different ways of doing that, but I guess that's what companies do well, is to advertise themselves, to really sell themselves.
It is, yeah. Well, actually, like I feel like one of the reasons on this podcast, and so like I don't have an official role in the company, and one of the reasons for this was also that it's interesting because when you come from like you're running a company, it makes sense that they're promoting their own product and their own vision, which totally makes sense. But there's also a very important role for academics who have knowledge about what's going on, but are sufficiently distant from it that they're not fully only self-motivated just by their own, projects or so
Sure.
forth. And for me, this is, I mean, we see particularly the problems of the distrust in technology, and then honestly in the scientific community as well too. It will be one of the greatest tragedies, I would say, that if we go through all of this and almost pull off what looks like a miracle, like technologic and scientific wise, which is to make a fusion power plant, and then nobody wants to use it because they feel that they don't trust the people who are doing it or the technology. So we have to get so far out ahead of this. So I give lots of public lectures or things like this of accessing a larger range of people. We're not trying to hide anything. You can come and see, come do tours of our laboratory. In fact, I want to set those up virtually as well too. You might look at our Plasma Science and Fusion Center YouTube channel. So we are reaching out through those media,
Great.
and it's really important that we do those things. But it's also then realizing, setting up the realistic expectations of what we need to do. We're not there. We don't have commercial fusion devices yet. And you asked, what are the challenges? I'm not going to get into any deep technical, questions about what the challenges are, but the pathway, not just to make fusion work technically, but to make it economically competitive and viable so that it's actually used out in the private sector, is a non-trivial task. And it's because of the newness of it. We're simultaneously trying to evolve the technology and make it economically viable at the same time. Those are two difficult coupled tasks. So my own research and my own drive right now is that fantastic Commonwealth Fusion Systems is set up. We have a commercialization unit of that particular kind, which is going to drive forward a tokamak. In fact, I was just there's discussions, or there's dialogues going on around the world with other kinds of ones like stellarators, and which prefer different kinds of challenges and economic advantages. But I know what we have to have. What we have to have is a new generation of integrated scientists, technologists, and engineers that understand what needs to get done to get all the way to the goal line. Because we don't have them now.
So a multidisciplinary team.
Yeah, exactly.
What's required? I mean, you've spoken about. You said that fusion is, quote, the most multidisciplinary field you can imagine.
Yes. Yeah.
Why is that? What are the differences?
Yeah, well, because most of our discussion that we've had so far is really like a physics discussion, really. So, which don't neglect physics, is at the origin of this. But already we touched on plasma physics and nuclear physics, which are basically two, somewhat overlap but independent disciplines. Then when it comes to the engineering, it's almost everything. So why is this? Well, let's build an electromagnet together. Okay. What is this going to take? It's going to take, it's basically electrical engineering, so you understand how it goes together, what happens. Computational engineering to model this very complex integrated thing. Materials engineering, because you're pushing materials to their limit with respect to stress and so forth. It takes cryogenic engineering, which is sort of a subdiscipline, but cooling things to extremely low temperatures.
There's probably some kind of chemistry thing in there too.
Well, actually, yeah, which tends to show up in the materials, and that's just one of the subcomponents of it. Almost everything gets hit in this, right? So you're also in a very integrated environment, because in the end, all of these things, while you isolate them from each other in a physics sense, in an engineering sense, they all have to work seamlessly together. So it's one of those. In my own career, I've basically done atomic physics, spectroscopy, plasma physics, ion etching, so this includes material science, something called MHD, magnetohydrodynamics, and now all the way through, I'm not even sure how many different careers I've had. It's also, by the way, this is also a recruiting stage for young scientists thinking to come in. My comment to scientists, if you're bored in fusion, you're not paying attention, because there's always something interesting to go and do. So that's a really important part of what we're doing, which isn't new in fusion actually, and in fact is in the roots of what we've done at MIT. But holy cow, the proximity of possibility of commercial fusion is the new thing. So my catchphrase is, like, you maybe wonder, like, why weren't we doing all these things? Like, why weren't we pushing towards economic fusion and new materials and new methods of heat extraction and so forth? Because everybody knew fusion was 40 years away. And now it's 4 years away.
There is a history, like you said, 40, 30, whatever, the kind of old joke. There's a history of fusion projects that, are characterized by cost overruns and delays.
Yeah.
How do you avoid this? How do you minimize the chance of this?
You have to build great teams, is one of them. It tends to be that the smaller there's sort of I'm not an expert in this, but I've seen this enough integrated.
Is there an equation?
Yeah. Well, I've seen this from enough teams. Like, I've seen also the futility of lone geniuses trying to solve everything by themselves. Like, no. But also organizations that have 10,000 people in them is just doesn't lend itself at all to innovation. So, like, one of our original sponsors and a good friend, Vinod Khosla. I don't know if you've ever talked to Vinod Khosla. He's a venture guy. He's got fantastic ideas about, like, the right sizes of teams and things that really innovate, right? And there is an optimum place in there, is that you get enough cross-discipline and ideas, but it doesn't become so overly bureaucratic that you can't execute on it. So one of the ways, and this was one of the challenges of fusion, is that everything was leading towards, like, I have to have, like, enormously large, like, teams just to execute because of the scale of the project. The fact that now, through both technology and I would argue financing, innovation, we're driving to the point where it's smaller, focused teams about doing those things. So that's one way to make it faster. The other way to make it faster is modularize the problem or parse the problem. So this is the other difficulty in fusion, is that you tend to look at this as like, oh, it's really just about making the plasma into this state, here, that you get this energy gain. No. Because in the end, if you can parse out the different problems of making that and then make it as separate as possible from extracting the energy and then converting it into electricity, the more separate those are, the better they are, because you get parallel paths that basically mitigate risk. This is not new in fusion, by the way, and this is the way that we attack most complex technological, integrated technological challenges.
Have you, by any chance, seen some of the application of artificial intelligence, reinforcement learning? DeepMind has a nice paper, has a nice effort on basically using reinforcement learning for a learned control algorithm for controlling nuclear fusion.
Yeah.
Do you find those kinds of, I guess you throw them under the umbrella of computational modeling. Do you find those interesting, promising directions?
They're all interesting. So when people, I'll pull back. Maybe a natural question is, like, why is it different in fusion? Like, there's a long history to fusion, right? It was going on for, like I told you, like, stories from the late 1960s. Like, what's different now, right? So I think from the technology point of view, there's two massive things which are different. So one of them, I'll be parochial. It's the advent of this new superconducting materials, because the most mature ways that we understand about how we're going to get to fusion power plants are magnetic fusion. And by the fact that you've got access to something which, like, changes the economic equation by an order magnitude, is just a totally, and that wasn't that long ago. It was only September of 2021 that we actually demonstrated the technology. That changes the prospects there. And the other one is computing. And it's across the whole spectrum. It's not just in control of the fusion device. It's actually we actually use machine learning and things like this in the design of the magnet itself. It's an incredibly complex design space. So you use those tools. The simulation of the plasma itself is actually, we're at a totally different place than we were because of those things. So those are the two big drivers that I see, actually, that make it different. And it's interesting, both those things self-enforce about what you asked about before, like, how do you avoid delays and things? Well, it's by having smaller teams that can actually execute on those. But now you can do this because the new magnets make the devices all smaller, and the computing means your human effectiveness about exploring the optimization space is way better. It's like they're all interlinked to each other.
Plus the modularization, like you said, and everything just kind of works together to make smaller teams more effective, move faster.
And it's actually, and it's through that learned experience. I mean, of the things that I'm the most proud of about what came out. In fact, the origins of thinking about how we would use the high temperature superconducting magnets came out of my design class at MIT. And in the design class, like one of the features that I kept, I mean, it was interesting. I really learned along with the students about this, but like this insistence on the features, like we can't have so many coupled, integrated, hard technology developments. Like we have to separate these somehow. So we worked at this. And in fact, that's what really, in my opinion, the greatest advantage of the ARC design and and built into the Commonwealth Fusion System idea is like to parse out the problems. Like how can we attack these in parallel? And so it really comes to we talked about philosophy. It's like a design philosophy. Like how do you attack these kinds of problems? And you do it like that.
And also, like you mentioned offline, that there's a power to, as part of a class, to design a nuclear fusion power plant.
Well,
and then make it a reality.
And it's hard to imagine a more powerful force than like 15 MIT PhD students like working together towards solving a problem. And what I always, in fact, we recently just taught the most recent. I say I teach it. I mean, I guide it actually. Yeah. The most recent version of this, where they actually designed, based on this National Academies report, they actually designed like a pilot plant that has basis and similarities to what we had done before. But, I kept wanting to like push the envelope and where they are. It's like the creativity and the energy that they bring to these things is kind of like, it keeps me going. Like I'm not going to retire anytime soon when I keep seeing that kind of dedication, and it's wonderful around on that. It almost, not to overuse or to paraphrase something, right? Which is that, the famous quote by Margaret Mead, never doubt that a small group of dedicated, persons will change the world. Indeed, it's the only thing that ever has.
I mean, that's just such a powerful and inspiring thing for an individual. Find the right team, be part of that, and then you yourself, your passion, your efforts could actually make a big change.
Yeah.
A big impact.